We are still in Laplace transforms, so let us determine the Laplace transform of some more functions. So let us take the Laplace transform of t squared plus 3 quantity squared, right? So t squared plus 3 quantity squared when expanded becomes t raised to 4 plus 6t squared plus 9. So the Laplace transform of t squared plus 3 squared is the same as the Laplace transform of t to the 4th plus 6t squared plus 9. And we know that the Laplace transform of the sum is the same as the sum of their Laplace transform. So we take the Laplace transform of t raised to 4 plus the Laplace transform of 6t squared plus the Laplace transform of 9. So t to the 4th becomes 4 factorial over s raised to 4 plus 1 or 5 plus 6 is a constant which serves as a multiplier to the Laplace transform of t squared, which is 2 factorial over s raised to 2 plus 1 or 3 plus the Laplace transform of the constant 9 is 9 over s. So 4 factorial, that is 24 over s raised to 5 plus 6 times 2 factorial is 12 over s cubed plus 9 over s. We can write this as 1 over s raised to 5 times 24 plus 12s squared plus 9s to the 4th. Okay? Next, let us obtain the Laplace transform of cosine squared 3t. We have the Laplace transform for cosine but not for a power of cosine. So in here, we are going to apply an identity to cosine squared 3t, which is 1/2 the quantity 1 plus cosine of 2 times 3t or 60. So that is equivalent to 1/2 the Laplace transform of 1 plus cosine 60 equal to 1/2. The Laplace transform of 1 is 1 over s, and that of cosine 60 is s over s squared plus 6 squared. So that is 1/2 1 over s plus s all over s squared plus 36. Now let us combine this. 2s s squared plus 36, that becomes s squared plus 36 plus s squared. So that will be 2s squared plus 36 all over 2s s squared plus 36, or we can cancel 2. Okay, so that will be s squared plus 18 over s squared plus 36. Let us have another one. We take the Laplace transform of e to the 3t minus e to the negative 2t quantity squared. So that is the same as the Laplace transform of, we expand e to the 3t minus e to the negative 2t quantity squared into e to the 6t minus twice the product of e to the 3t and e to the negative 2t, which is e to the t, plus the square of e to the negative 2t, which is e to the negative 4t. Alright, so the Laplace transform of e to the 6t is 1 over s minus 6 minus 2 over the Laplace transform of e to the t is s minus 1 plus the Laplace transform of e to the negative 4t is 1 over s minus negative 4 or s plus 4. Okay? You can combine this. If you want, you can simplify this by combining these three fractions. How about the Laplace transform of, say, hyperbolic cosine of t over 3? Hyperbolic cosine of t over 3, that will be equal to s over s squared minus k squared. Your k here is 1/3 squared. So that will be equal to s squared minus 1 over 9, or 9s squared minus 1 over 9, which goes up and combines with s. So 9s over 9s squared minus 1. Let us have another one. The Laplace transform of sine of the quantity 3 plus 2t. Okay, so the argument of sine is 3 plus 2t. So let us recall an identity, a trigonometric identity, that says that sine A plus B is equal to sine A cosine B plus cosine A sine of B. Okay, that is an identity. So here, our A is 3 and our B is 2t. So we shall now write this as the Laplace transform of sine A, that will be sine of 3 cosine of 2t, plus cosine of 3 sine of 2t. So sine 3 and cosine 3 are both constants. So sine 3, the Laplace transform of cosine 2t is s over s squared plus 2 squared, plus cosine of 3, the Laplace transform of sine 2t is 2 over s squared plus 2 squared. So that will be equal to s sine of 3 plus 2 cosine of 3 over s squared plus 4. Okay? Let us go now to the shifting theorem. That says that the Laplace transform of e to the at f of t is equal to f of s, the Laplace transform of f of t, with s transformed to s minus a. Okay? We know that the Laplace transform of f of t is denoted by f of s. Okay? The Laplace transform of f of t is f of s. So the Laplace transform of e to the at f t is f of s. Take the Laplace transform of f of t, which is f of s, and you change s to s minus a. So let's go over the proof. The Laplace transform of e to the at f of t, using the definition of Laplace transform e to the negative st times f of t. This is your entire function, e to the at f of t dt. And we can combine e to the negative st e to the at as e to the negative quantity s minus a t f of t dt. And we recognize this as the Laplace transform of f of t with which is f of s, okay, the Laplace transform of f of t which is f of s, but s changes to s minus a. Alright, so let us have an example. We take the Laplace transform of e to the 2t times t squared. Alright, we are going to suppress e to the 2t and let f of t be equal to t squared. And the Laplace transform of f of t will be equal to 2 over s cubed, or 2 factorial over s raised to 2 plus 1, 2 over s cubed. So, the Laplace transform of e to the 2t times t squared will be 2 over s cubed, but we have to change s to s minus, what is my a here? E to the 2t, so my a is equal to 2. Okay, so that is my a. So s is changed to s minus 2. So the answer here will be 2 over s minus 2 quantity cubed. Another example. The Laplace transform of e to the negative 3t sine of 2t. So here, our f of t is e to the, or rather, sine of 2t. So we suppress, no? We suppress e to the at. The rest will be our f of t. So f of t is sine 2t. So we take the Laplace transform of f of t, which is equal to 2 over s squared plus 2 squared, or 4. So this will be equal to 2 all over s squared plus 4, but we have to change s to s minus negative 3 or s plus 3. So this becomes 2 over s becomes s plus 3 squared plus 4, or 2 over s squared plus 6s plus 9 plus 4, that will be 13. Okay, so that is the shifting theorem. Next, we get the Laplace transform of the derivative. Laplace transform of derivatives. Okay. We want to find the Laplace transform of f prime of t. So the definition, the Laplace transform of f prime of t will be equal to the integral of e to the negative st f prime of t dt 0 to infinity. So we apply integration by parts. Our u is e to the negative st, and our dv is f prime of t dt. So our du is Negative s is a constant, so negative s e to the negative st dt. While b will be the integral of f prime of t dt, which is simply f of t. Alright? So this then will become uv e to the negative st f of t from 0 to infinity minus negative, so positive s integral of e to the negative st f of t dt. Alright, substituting the upper limit because e to the negative s, because we have e to the negative st, that will be 0 minus the lower limit. Substitute 0 to t, e to the negative s times 0 is e to the 0 or 1 times f of t, but t is replaced by 0, so that is f of 0. Plus s integral of e to the negative st ft dt from 0 to infinity, that will be s. And we recognize this as the Laplace transform of f of t, which is f of s. So that becomes s f of s minus f of 0. So that is the Laplace transform of f prime of t. So at this point, we are only concerned with the notation, no, of the Laplace transform of f prime of t. Similarly, the Laplace transform of the second derivative of t will be equal to s squared f of s minus s f of 0 minus f prime of 0. There. So if you want, in general, the Laplace transform of the nth derivative of t, that will be equal to s to the n f of s minus s to the n minus 1 f of 0 minus s to the n minus 2 f prime of 0 minus, and so on and so forth, minus f raised to n minus first derivative of 0. There. Okay? So we'll be using this notation in solving differential equations using Laplace transforms. Next, there is a theorem, an important theorem, the Laplace transform of, or t multiplied transform. Okay? T multiplied transform. This will help us evaluate the Laplace transform of t times f of t. Okay? The Laplace transform of t f of t. So it says that the Laplace transform of t f of t is equal to negative times the derivative of the Laplace transform of f of t. Okay? So f of s is the Laplace transform of f of t. This formula tells us that if you have a t multiplied function f of t, you can suppress t, take the Laplace transform of f of t, which is f of s, and then get its derivative. Alright? So disregard the t, get the Laplace transform of f of t, which is f of s, and get its derivative, multiply it by 1. Okay. So as for the proof, let the Laplace transform of f of t be equal to f of s. So the integral of e to the negative st f of t dt from 0 to infinity is f of s. We now take the derivative. No? We take the derivative with respect to s of both sides. So we get the derivative with respect to s of both sides. So what do we have? We are differentiating with respect to s. So that will be the integral from 0 to infinity e to the negative st. The derivative with respect to s will be negative t. E to the negative st f of t dt equal to f prime of s. Alright? Or negative of the integral from 0 to infinity of e to the negative st times t f of t dt, which is equal to f of s or f prime of s. So multiplying both sides by a negative sign, 0 to infinity, e to the negative st, t f of t dt is equal to negative f prime of s. And we recognize this, the left side, we recognize this t f of t as the function, and that is the Laplace transform of t f of t equal to negative f prime of s. Alright? So similarly, the Laplace transform of t squared f of t will be equal to negative 1 squared second derivative of f of s. So suppress t squared, get the Laplace transform of f of t, which is f of s, get its second derivative. No? The order of the derivative is dictated by the exponent of or the power of t. Since it is a power 2, you differentiate twice. And the factor negative 1 is raised to the power of 2. And generally, the Laplace transform of t to the n of f of t will be equal to negative 1 raised to n, and the nth derivative of f of s. Okay? So if you want to find the Laplace transform of t multiplied function f of t, you simply take the negative of the derivative of the Laplace transform of f of t. So let us have an example. Take the Laplace transform of t sine of t. Okay. So let f of t be equal to sine of t. You suppress, no? You suppress t, and that will be the remaining factor will be your f of t. Then take the Laplace transform of f of t. The Laplace transform of sine t is equal to k, which is 1 over s squared plus 1 squared over 1. So, the Laplace transform of t sine of t is equal to the derivative, negative, the derivative of 1 over s squared plus 1 with respect to s. Okay? We suppress the t. We took the Laplace transform of sine t, which is 1 over s squared plus 1. For the Laplace transform of the function t sine t, it will be the first derivative of 1 over s squared plus 1 times negative 1. So that will give us, so we apply the quotient rule. in finding the derivative of 1 over s squared plus 1. So that is the same, by the way, that will be the same as s squared plus 1 raised to negative 1. Alright, so negative power formula, negative s squared plus 1 raised to negative 2 times the derivative of s squared, which is 2s. So negative and negative, that will be positive 2s over s squared plus 1 squared. Okay? How about this one? The Laplace transform of t squared e to the 2t. We can find the Laplace transform of t squared e to the 2t using the shifting theorem. Alright? But instead of using the shifting theorem, let us apply the t multiplied transform. Okay? The t multiplied transform. So, let f of t be equal to e to the 2t. So what is my f of s? The Laplace transform of e to the 2t. It will be 1 over s minus 2. Since the power of t is 2, that will be the Laplace transform of t squared e to the 2t will be negative 1 raised to 2. And then the second derivative of 1 over s minus 2 with respect to s. Alright? So negative 1 squared is of course positive. The first derivative of 1 over s minus 2. Okay, so let us solve that separately. Your f of s is 1 over s minus 2. So let us get the first derivative. Use the power formula. That will be negative 1 over s minus 2 squared. Then the second derivative, that will be positive 2 over s minus 2 cubed. Okay? So the answer here will be equal to negative 1 squared or positive 1, 2 over s minus 2 quantity cubed. Okay, that is the Laplace transform of t squared e to the 2t. Let us apply the shifting theorem. Use shifting theorem. So, the Laplace transform of t squared is, the Laplace transform of t squared is 2 factorial over s raised to 2 plus 1. And then, the Laplace transform of t squared e to the 2t will be 2 over s minus s cubed, but s is changed to s minus 2. So that will be 2 over s minus 2 cubed, which agrees perfectly with our answer. Whether we use the shifting theorem or the t multiply transform, we'll be getting the same Laplace transform. Okay? Let us have another one. Let us take the Laplace transform of t e to the, let me see, e to the negative t cosine of t. Alright, so this will be a combination of what? T, e to the negative t, and cosine t. Alright? So we treat this as a t multiplied transform. So we shall let our f of t be equal to e to the negative t cosine of t. Okay? Suppress the t. We suppress the t, and what remains is our f of t, e to the negative t cosine t. Then, we take the Laplace transform. We take the Laplace transform of f of t. So your f of s here will be, okay, we can use here the shifting theorem. Suppress e to the negative t. Take the Laplace transform of cosine of t and change s to s minus negative 1 or s plus 1. The Laplace transform of cosine t is s over s squared plus 1 squared. But we need to change s to s plus 1. So that will be s plus 1 over s plus 1 squared plus 1 or s plus 1 over s squared plus 2s plus 1 plus 1 or plus 2. That is my f of s. And apply the t multiply transform. That will be negative of the derivative of s plus 1 over s squared plus 2s plus 2 with respect to s. So negative. Then we apply the quotient rule. So s squared plus 2s plus 2 squared. Derivative of the numerator s plus 1 is 1 multiplied by the denominator s squared plus 2s plus 2 minus the numerator s plus 1 multiplied by the derivative of the denominator, which is 2s plus 2. Okay? So, negative of the quantity s squared plus 2s plus 2 minus 2s cubed or 2s squared. Now, we multiply s plus 1 and 2s plus 2. So, that will be 2s squared plus, okay, there. So minus, we multiply first s plus 1 and 2s plus 1. So that will be 2s squared plus 4s plus 2 over s squared plus 2s plus 2 quantity squared. So negative of the quantity. S squared minus 2s squared is negative s squared. 2s minus 4s is negative 2s. 2 minus 2 will cancel. Okay? So s squared plus 2s plus 2. And then we can factor the negative sign. Combines with the negative sign, it will be positive. And then we factor s. So that will be s plus 2 over, is supposed to be to the power of 2. S squared plus 2s plus 2 squared. Okay, so that is the Laplace transform of t e to the negative t cosine of t. So we applied two theorems here, the t multiply transform and the shifting theorem.